Today we are going to discuss unsupervised machine learning models, and more specifically clustering models. My name is Sumudhu Tenakon. I'm a data scientist. I'll be helping you through these lessons to navigate your data science and AI career. In our machine learning introduction lesson, we learn different types of training approaches, or we can call them machine learning approaches: supervised, unsupervised, and reinforcement learning. We learned about supervised learning algorithms in our previous lesson. Today, our topic is about unsupervised machine learning. We are not going to discuss reinforcement learning in this course, but we can discuss in another advanced course in a later time. Before we jumping into the topic discussing unsupervised machine learning, let's first understand what are the key differences between supervised and unsupervised learning. In supervised learning, we are using labeled data sets. What are those labels? Those labels are the ones we have known outputs or known outcomes for given set of features. We call it ground truth, or we can call them as target variable or Y values. In classification models, we predict a class as the output. In regression models, we predict a number or numeric value as the output. We learned about these things in detail in our previous lessons. When we talk about unsupervised learning, we are not going to use labeled datasets as we used in supervised learning. Instead, we are going to use dataset with features. Therefore, no dependent or target variable in unsupervised learning. For example, in clustering method, the process starts with the collection of variables. So we provide set of variables from different objects. We can just assume that to find out the similarity between them and classify them into clusters or groups. So those who have similar characteristics based on their features, they will be grouped together into clusters. How many clusters we wanted to have in our data set, that's something we can control. We are going to discuss this in detail in our coming slides. We learn about how the machine learning models are being trained and used with the supervised learning. This exact slide you have seen in our previous lesson. In supervised learning, we use training data or features with known output, or we can call it ground truth or Y variable or target variable. And then your model get trained based on the features and your Y variable. And then the trained model will be your output of the model training process. How we use the model in a production environment or to serve the model to user through application, we are going to get user input in terms of features, and then the model will process user data and predict a result. So that predicted result will be the outcome of your model. So that is the general way of your machine learning model building and how it being used in a supervised machine learning. So what is the difference between supervised and unsupervised in this diagram? So in unsupervised learning, we are not going to provide the known outcome or Y variable as we discussed in the previous slide. Your model is trained based on the features, like already we discussed that. The usage of the model can be same as your supervised machine learning model. You still have the model as the output of the training process. You're using the data, and your model will process the data and give you the output. For example, in a clustering model, your output will be the cluster number or cluster label. We discussed different types of machine learning algorithms in our previous lesson as well. We have regression and classification. They are supervised machine learning models. Under regression, we learn linear regression, polynomial regression, and we also learned there are many different types of regression models involved. And for classification type of machine learning problems, we can use tree-based classifiers, logistic regression, support vector machines, and many other classification algorithms. For unsupervised learning, clustering is one example for unsupervised learning we will be covering in this lesson. We will cover different algorithms. A couple of algorithms I mentioned here, k-means clustering and dbScan. We will learn about these things in detail in the coming slides. This is also a familiar slide from supervised learning. In supervised learning, we try to understand our model as a mathematical equation which accepts features as x variables and returns the y variable as the prediction. So we can do the same thing for classification model. So we can think the features, you are sending the features into the model and then you are returning the prediction as the output, as the y variable. So that will give you the cluster number or a label you assign to each cluster. Let's try to understand different types of clustering you can find when you wanted to decide on applying clustering algorithm on your machine learning problem. This taxonomy is not a standard one. You can find in many different variations of it, but I try to combine multiple different sources and try to build one as everybody can understand. You can find out different types of clustering algorithms which can fall into two main categories, hierarchical and non-hierarchical. And we can also find grid-based clustering algorithms as well. In non-hierarchical, we can call like flat clustering. We can find centroid or partitioning based, and we can find distribution based, and we can find density based clustering. For the hierarchical ones, first of all, let's try to understand a little further. So in the centroid or partitioning based clustering, one example is k-means clustering, as you see in this diagram on your right side. So you can find blobs, two blobs, one in orange and one in blue. So you can find out the center of each blob can be determined using clustering algorithm, and you can draw a centroid around that center, and then everything within that centroid will be considered as the data points belong to that cluster. That's how you can divide. So this is a simple description, but we will go into very detail about how this actually happens. A distribution based clustering, we can use kind of a probability notion there. So that has a soft boundary than the hard boundary of centroid we had in the centroid based partitioning. So your decision of like whether a data point belongs to a cluster or not based on what is the likeliness to be in one of the cluster, right? So we can give as a probability. So the density based clustering, we are using a density based approach. So in one of the key difference between other clustering and density based clustering, you can find the black dots outside the regular two clusters. Those are outliers, so we can call them as noise. So we can get if any point is not going to belong to a cluster strictly, so we can mark them as noise, or the dbScan algorithm will mark them as noise. Okay, so that's about non-hierarchical clustering. The hierarchical clustering, we can have agglomerative or divisive. So what they mean? The first one mean like you are taking a bottom-up approach. So means you are starting with your data points and trying to group them, and you are building clusters. You are starting from the bottom and you are trying to build the clusters from bottom to top. You can decide when to stop. So we will discuss this in detail in one of our slides later. But for a general understanding, so you can decide when to stop. So if you wanted to stop at 3 clusters, you can simply let your algorithms to stop. If you wanted to stop at after making 2 clusters, so you are creating superclusters and superclusters of those clusters, you can stop at that point. Right? In the divisive method, you're starting with the supercluster and you are further dividing into subclusters. So you're starting from top to bottom, as the name suggests. You have like one example you have seen in the slide in the rightmost corner. You can find there's a supercluster, and within that you can find some subclusters. Okay. A grid-based clustering also being used in many different applications. Today we are not going to discuss in this lesson, but you can find it and many other resources discussing grid-based clustering. Clustering is unsupervised learning, as we already identified. What clustering does is grouping data points based on their similarities. In this diagram, you can see the clustering happened based on the color. Even the objects in this diagram are different shapes or different sizes of the same shape. They belong to same cluster because the similarity how they measure is by the color. So for the actual clustering algorithms, you are doing like you're checking more parameters than the color. Your problem is much more complex than the simple clustering, but you can understand what is actually happening here. The consideration for clustering, you have to have your cluster should be representation with more than one data point. To have a cluster, you have to have at least two data points. That means if you have one data point, probably it's not a good idea to call it a group, just an individual observation or record or data point. If you have more data points, that's how you can make a cluster. How we define the qualification for a data point to be a member of a cluster or nearness is a consideration. So you need to define how you make, for example, in this slide, I mentioned the color is the parameter we will be using. If two objects having similar color, maybe different variation of yellow still qualified to be in the same cluster, right? Different variation of red belongs to, even the object has different variation of red, can belongs to the same cluster as red. So how you define that nearness? It's a consideration you need to have when you are deciding about the clustering application. And also when to stop the data points assignment to cluster. So you can run a clustering algorithm, and like we already saw in the hierarchical clustering. So you have to define, or you have to give explicit instruction to your algorithm when to stop. If you wanted to have more clusters than what you need, probably your application, if you're going to have more clusters than what you need, your application will not help. If you really wanted to get 2 clusters, if your algorithm will give you 4 different clusters, probably then you need to regroup or combine 2 groups, and you have to do some extra work. But if you start with a definite number of clusters, you instruct your algorithm to do like give me 2 clusters, so your algorithm will do that work for you. So therefore, stopping criteria should be a must when you are deciding or when you are working on a clustering problems. Okay, so here we are trying to understand a clustering example. We went to this example in one of our very first lessons. Here our goal is to cluster set of fruits given to you. Maybe you think like you can have a set of bunch of fruits on a table. Your task is to group them based on the similarity. As a human, you can identify by the appearance. This is apple, this is pineapple, this is banana, this is orange, etc. But think how machine can do it. So in our very first lessons, we discussed about classifying fruits by 3 parameters: color, diameter, and weight. So we can apply the same thing here. So assume a machine learning algorithm is employed here to group the fruit by their similarities. So let it run. What it does is this machine learning algorithm will create clusters and group similar fruits together. In that case, apples, based on the characteristics, apple can group into one cluster, and pineapple can group into one cluster, blueberries into another one, strawberry into another one, banana into another one. Okay, so now let's compare this with the classification example we discussed with the same domain. So when we are using a classification machine learning algorithm, you can classify these fruits by the label, right? You can know, okay, these are the set of fruits, they are apples. You can say these are the set of fruits, they are pineapples. These are the set of fruits, they are strawberries. You can definitely tell which class they belongs to, because you are training with features as well as known class for each fruit. But in this example, we are not going to send the known class. Therefore, what your algorithm can do is, your clustering algorithm can do is cluster them based on the similarity. It will identify different clusters, but your algorithm will not tell you which cluster each fruit belongs to, or like the label of the cluster, right? You can say cluster 1 belongs to set of fruits, with the similar characteristics, but your algorithm will not tell you they are apples. You have to apply some domain understanding or another layer of your application to label them as apple. Maybe you have to apply another classification algorithm. But what I need to tell you here is the clustering will not give you labels, but it will give you cluster labels. You can know this is one cluster, this is another cluster. Okay, but it will not give you a definite name that item below the class that item belongs to. Okay, let's try to look at one more example. Think of an example of cricket player statistics. Okay, so this kind of a made up plot, but you can understand what it is going to tell you. If I wanted to plot the runs a player take and the wickets that player take during its lifetime, or within, like, say, assume to be fair, let's assume it's within last year. Okay, so the x-axis will define how many runs a player accumulated in that year, and y-axis will tell how many wickets that player took during that year. Each dot represents a player. Okay, so for example, if you take this player, so this player, I don't have a numeric value, I just wanted to be more general here. So this player got this much wickets, whatever the number coming from this y-axis, and this much runs in that year, right? The player like this guy, he or she got this much runs according to the scale of this x-axis, but no wickets. That's what we can safely assume. Okay, so now what we can do with this data? So we have this data set. So what we can do now? So we can apply this data set to a clustering algorithm, and then we can build different clusters. So what is our goal is to build two different clusters based on these characteristics. So in this data set, remember, we have only two variables: number of wickets, how many runs. So let's try to apply a clustering algorithm. So it can make one cluster of based on the similarity of these this player represented by dots based on their similarity. So they have what is the common characteristics: low runs but high wickets. They are close by in this cluster. A second cluster we can take out are the players who have low wickets but high runs. So they also these data points are close by, so they can make within a centroid. What happened to these three guys? So they are kind of outliers. So right now you cannot put them into any cluster with the rule set we wanted to make these clusters, right? So they are not going to match any rule. I don't specify which clustering method it is, but in general, so we cannot fit them into a cluster. We can call them as noise. But in cricket domain understanding about the cricket, you can think of they are all rounders. They get wickets and runs both. You can think like that. Alright, so now you have an understanding how the clustering method can work and how you can apply into a real data set. Let's try to understand some of the applications of clustering. Clustering is very useful for market and customer segmentation. If you want to group your customer base into different groups of people having similar characteristics, and then you have to roll in your marketing campaign. So each group will receive your marketing or promotional materials differently than the other group. Maybe the marketing materials are very customized to the common characteristics of those groups. So for that purpose, clustering will be very useful. What you will have in your data set, you can have the customer details such as age, maybe their job role, or maybe the area they live, or maybe their buying pattern, right? If you are working for a retailer, if you are letting your customer buy items online, you know what type of items they usually buy. Based on those buying habits or buying patterns, you can group the similar customers. And if you wanted to put a marketing campaign to sell a specific product, so you can customize your marketing advertisement or the promotional material to that cluster. Clustering can also be part of recommendation engines. So we discussed about recommendation engines very briefly in one of our very first lessons. So in the recommendation engines, you can use clustering to group your customers, very similar to the example I just described, and then based on that customer groups, you can find out their characteristic, what they like, what they don't like, and then you can suggest another person in the same group, but you don't know that person bought this item or whether they like or not, so you can assume he or she having the similar characteristics as other people in that group, and you can suggest that person about a product or some service. Clustering can also be useful in anomaly detection, like we already saw. You can find out what some outliers in a data set, also from clustering. Clustering is useful in medical data analysis if you wanted to analyze images, medical images such as X-ray diagrams, ultrasound diagrams, and many other medical diagnostic images. You can use clustering algorithms to group them and to study about a disease. So this will also help you in disease control for many different applications. You can read about the application of clustering in disease control and medical images. You can find many interesting articles about that. Clustering can also be useful in data labeling in our machine learning or data science work. Assume you get a data set without proper labeling. Right? If you have a data set with labeled and unlabeled data, but you wanted to use them in supervised machine learning, you need to have all the data properly labeled. One thing you can do is you can run a clustering algorithm is to build clusters. Assume you are expecting 3 different classes in your data set as a classification problem. Assume that, and then you are making 3 clusters out of your feature data set, and then you know for each cluster you find what is the label for each cluster. You can identify that because you have that information, but those clusters may have labeled and unlabeled records. Then you can safely assume, okay, the labeled records, you're having class 1 and other items in the same cluster without label, you can try to assign class 1 for the unlabeled records, and you can move forward with some experimental step with the model building, and then you have like more labeled data, right? So this is something you have to do gradually, incrementally, and experimentally, right? Sometimes it will work, sometimes you need to get some educated guesses, or you need to do some careful study to make sure that clustering will work in the labeling, but it is kind of a possible application. Clustering can also be used to understand subgroups exist in data. This can be applied in scientific research or medical research as well. So if you group your observation into subgroups, and then you can study each subgroup separately and understand each group and then understand their characteristics, right? And then you can find out how each group is separated or together. Sometimes we find 2 different clusters. If they are very close by, probably we can assume they are very close by, probably that we can consider that as a one cluster. If they are very far away from our quantification, so we can identify them as the clusters, very distinct clusters, right? So some of the characteristics are very important in research, in scientific research, to do apply clustering. Okay, so these are some applications of clustering. So we will discuss more when we are exploring our practical examples. Centroid-based clustering. Assume you have a data set like you have seen in the screen right now. You have x1 and x2 axes. So each data point will be displayed in same color gray. You don't have any cluster defined here. Now assume you wanted to make 2 clusters out of it. If we apply centroid-based clustering, so this is what you're going to get. You get the cluster center represented by a cross. So you have the orange cross and the blue cross on the screen right now, and each data point close by this cluster center will belong to the cluster. So this is what we call as a k nearest neighbor clustering. So we can have k, the number of clusters is 2. So let's try to understand how it works. So when you apply this type of clustering, you wanted to know, or you wanted to choose how many number of clusters you want. And a cluster is determined by centroid and its center point. Like I mentioned, the center point of this cluster is represented by a cross in this diagram. Whether or not a point belongs to a cluster is determined by Euclidean distance. Mean like if the distance from this center point to your data point is further away, you can say this point is not belong to that cluster. If it is closer to another cluster, that belongs to that cluster. So based on the distance between the center point and each point will be assigned to a cluster. In this method, each point must be assigned to a cluster, or each point will be assigned to a cluster. Items enclosed within hard boundary will be the boundary of the cluster. So this is a hard boundary. This clustering method is not good for a non-circular shape clusters. For example, if you have an elongated shape in one of the cluster, you probably will not get good result if you are using this centroid based clustering. Let's try to explore this centroid based clustering step by step. So you will find the step 1 here. The step 1 is to place the k centroids in random locations. Assume you place the blue cross and orange cross in random locations. The orange cross is denoted by CO and the blue cross denoted by CB in this diagram. The distance between the 2 points we are trying to focus in this diagram. So distance between the point in the leftmost side with the orange cross will be DIO, and the distance between the second point towards the right side will be DJO. Similarly, the distance between the blue cross and each point will be DIB and DJP. So using these two parameters per point, we can define, okay, so let's take the first point towards right here. So what is the shortest distance between DIO and DIB? It's obvious, it's this DIO. So what is that distance defined? The distance between orange cross and the data point. So that makes this point belongs to orange cluster, or belongs to the orange color or orange cross. The other data point DJO and DJB. What is the shortest? DJB. So that means that the data point towards your right side belongs to the blue cluster. So let's try to apply. Step 2 will do that task. Calculate the distance between each point to the centroid center, and then step 3, find the nearest centroid, and that will apply your cluster color to that. So now we can safely label them. Those 2 data points belong to each cluster. So this process will go on until you get all the data points assigned to each cluster. So that's the first iteration. Okay, so after you do the first iteration, this is what you get. You get blue cluster and the orange cluster. So now what is going to happen is, initially you remember our blue cross was somewhere here, orange cross was somewhere here. Therefore, this data point assigned to blue cluster initially. Alright, so in that case, this data point previously labeled as blue data point belongs to blue cluster. So now what happened in the next step, right? We are going to calculate in the step number 4, we are going to calculate a new center, mean of all assigned points. So you have to find, so based on your all blue data points, we wanted to find a center point. So did physics, so you know center of gravity. So you can apply a method to find out what is the center point for all these data points. So that this new center point for blue cluster will be this. New center point for orange cluster is this. So now what you can do is, you can calculate again the distance between new center points and distance with each data point. The same method you apply, you can run it as a loop. The least distance from any cluster to that data point will determine which cluster this data point belongs to. So in the new under the new center points, so this blue data point will change into orange cluster, but because it has the shortest distance is now DIO than DIB. So now it's going to assign to orange cluster. Let's see that assignment. So this is after executing the second iteration. This is what's going to happen. You have two new centers and you have all the data points assigned. You can keep doing that until you reach into the stop point. Okay, so that is about the centroid based clustering. So now let's look at distribution clustering. In distribution clustering, we can consider that as an extension of k-means clustering or centroid based clustering we discussed earlier. In this method, a cluster is defined as a Gaussian distribution. You can see on the top right corner of this slide, two Gaussian distributions define two different clusters. If you think of the Gaussian distribution, you can think the higher at the peak of the Gaussian distribution is the highest probability at the center of the exact center point of that distribution. So in this method, a cluster defines a Gaussian distribution or mixture of Gaussian distribution that describe the likelihood of a point in each region belong to that cluster. So what does that mean? Let's think like now two clusters we have. So the orange cross and blue cross define the cluster center. So we have one data point at the center of each cluster. So that has the highest probability. You can think of that is the center of the Gaussian distribution. So which has the highest probability. When you're going further away from that center, your probability is getting decayed, right? So your probability getting reduced. So when it's going to like very far away, so your probability is getting very low value. So when it gets close to that center, the probability is getting higher. To determine whether a point belongs to a cluster or not, we can get this probability value. For example, the point marked in this red arrow has a probability of 0.8 according to the Gaussian distribution. The value is 0.8 for the orange cluster. And the value coming from the blue Gaussian distribution for the blue cluster is 0.7. So therefore, we can safely assume this data point belongs to orange cluster, not the blue cluster. This is based on like a probability model. And also another characteristic of the distribution clustering is it creates a soft boundary of enclosed clusters, right? Remember, in the centroid based clustering, we had a hard boundary. The centroid will define the boundary of the cluster, but here we are defining a soft boundaries because we are giving like a probability value, right? Okay, so let's move into the next. In the density based clustering is another clustering method we're going to discuss today. Assume you have a data set like this. If you get a data set like this, you cannot clearly make clusters just by looking at the data set, because in the previous example you could. To make a density based clustering, you have to apply the density based method. So we are going to discuss here. So if you apply density based clustering to this problem, you will get a cluster, two clusters like this, and also you can see some outliers or noise points also coming out as a result. So in density-based clustering, we group points based on the density of their locations. The density means how closely they are located to each other. More points closely located we call high density. This is related and put in the same group. So this point is related to other points in the same group, and they are putting into the same group. So less dense point distribution less likely belong to the same group. So if you find like a point distribution is less dense, so they are less likely belong to the same group. So we will explore this this concept in a more detailed diagram in coming slide. The points does not belong to any cluster located in low density areas will be designated as noise or outliers. This is what happened to those gray color dots. We cannot assign them to any cluster, so we consider as noise or outliers. This clustering method is good for application with noise in your data. All right, so let's try to explore it further. Let's start with the one data point. So as it marked in this red cross. Okay, so what is the step one? The step one is to select random point previously unlabeled. So for the beginning of this exercise or beginning of the clustering, you have to pick one point. Initially, all points are marked as gray color, no labels, right? And in the step 2, you have to count the number of points enclosed within a defined region. So defined region is going to be a key role here. So that how we define a region. So we define a region by enclosed circle. To define a region of a circle, we need to define what is the radius of that circle. So this is one parameter of a density-based clustering we wanted to provide. What is the radius of the circle you wanted to consider? So that we call epsilon. So you can find in the bottom of the slide. So the epsilon is the circle of the radius that defines the region around each point. When you pick a point, we also assume we are drawing a circle with the radius epsilon. And then if that point need to be qualified as a core data point, we need to have n number of or minimum number of points within that region to qualify as a core point. So that n is also another parameter you have to provide to density-based clustering algorithm. If you find that n number of data points within that circle, you consider that data point as a core data point. Right? So that's what you have the logic in step number 3. If n is 0, the current means like the current data point is the only point in your data set without any nearby points. So we mark those points as noise. If n is less than n minimum, if it has at least one data point, we mark them as a boundary point or the border point. If n is greater than or equal to the n minimum or the number of data points you wanted to have with to qualify as a core data point, we name it as a core point. Then those core data points will initiate a cluster and then assign data point to the current cluster, that assign all the data points around that into the current cluster. Then we can move on with the data points in the cluster. Okay, to understand better the core points, border point, and noise, let's try to have a detailed understanding. Assume this is like set of data points. I don't have any axis or anything, but assume you have a set of data points in your data set. So let's try to make a determination of core point, border point, and noise from these data points. First, we have to define the radius of the circle, which is epsilon, and we can also specify n minimum is 4. You need to have at least 4 within enclosed region with radius epsilon to consider that point as a core point. So here we have 4 data points, and we can consider this as a core point. We can keep doing that. We can take the next data point within the group, and then we can consider that as another core data point, because we have 4 data points, 5 data points actually within the enclosed region. So then we can keep doing that. So we can find out this is another core point. We have 4 data points. What happened to this guy, the one in the very bottom of the screen? So that will become a border point because it is nearby to the core point within a given radius, but within that radius you cannot find any other point than on the one core point. So those are the border points. Right? But still they belong to your cluster. So you can keep doing that. You can isolate the border points. So then you'll have your data set is divided into core points and border points. So now let's look at the leftmost data point. We don't have any other nearby point that will consider as noise. How you can make the cluster now? You can enclose your core points and border points to that cluster. Okay, so that is how we make a cluster in density-based clustering. Let's try to understand the density-based clustering in more detail with next steps. So assume now you did this understanding core points, border points, and then you make the cluster like this. If you make the cluster, if you complete the cluster, so then you can say in the step number 4, if a point is a core point or a border point, go to step number 2, right? So you can have to get the count of the number. So this is what we already discussed, and then you have to go through the step 3 and move forward. If the point is an outlier, so go to step number 1. If you found an outlier point, you cannot go to other steps, so you have to mark it as an outlier and then pick another random point. So you have to go as a loop. When you are going through the loop, you will flag all the data points belong to that cluster will be identified. So then you will automatically going to the next cluster, and then you will be grouping items belong to that cluster again. So if you complete all this orange, then you will be going to the next cluster. So you know this cluster and cannot connect to this cluster based on the criteria we use. You have to go through again the steps, and you will make the second cluster also. All right. So now let's look at another clustering method, hierarchical clustering. The same example we discussed about the centroid based clustering or distribution based clustering. We can assume the same data set for the hierarchical clustering. So here we have a data set. We don't know which cluster each of these data set belongs to. So let's try to understand, after applying clustering, what it could be. So once you apply the clustering, hierarchical clustering, you should find a superset or like a supercluster, and within that we can find subcluster. Right. So depending on the criteria you choose, you can decide to have like 2 clusters, 3 clusters, 4 clusters within one cluster, or you can decide when to stop the clustering. If it is bottom up, you can if the number of clusters, you can define number of subclusters. You can define if you're going top down in your depending on the algorithm you choose. The hierarchical clustering work well with the data, which can be represented as heat maps. You can generate dendrograms for this clustering, and the methods of hierarchical clustering we already briefly described earlier. The agglomerative or the bottom-up approach, or the divisive is the top-down approach. You can see the dendrogram as you've seen in the bottom right corner of the slide. We already saw that in the small diagram earlier. So you can start from the bottom and then group items together, and then similar items together, and then you can decide what is the cutting point or what is the stopping point for clustering. So in this example, if you went to the 2 cluster, if your stopping point is 2 clusters, you can safely group them into 2 clusters, right, or orange and blue clusters. Okay, let's try to explore the agglomerative clustering or bottom-up approach of hierarchical clustering. So what we have to do is we have to pick a data point, 2 data points. So we have to repeatedly combine 2 nearest clusters. So we have to find 2 nearest data points and make them as a cluster, and then we have to find another 2 set of data points, next one as make as the cluster, and you can keep doing that. And when you are making the one cluster, you can find the center point for each cluster, and then the distance between your center point and another data point, you can combine that nearest with the nearest data point. So that makes your second cluster. So now you have a center point for this 3 data point cluster. Then you can keep doing that until you make all the items added to the cluster, all the data points added to the cluster. If you wanted to cut after you create this dendrogram, you can decide when to cut down, or you can, when you are generating it, you can decide when to cut down if you are using bottom up approach, right? So here, like if you wanted to cut down at 2 clusters, so this is what you get. So now let's look at what are the clusters going to be selected. We have orange cluster and blue cluster coming out as a result of this bottom-up approach of hierarchical clustering. This will define a boundary between 2 clusters. And as you saw before, you can define any number of cutting points, so 2 clusters, 3 clusters, 4 clusters, etc. Now let's look at the divisive or like top-down approach of hierarchical clustering. This clustering recursively partitions your dataset into clusters. Stopping condition, you have to define how many clusters you have to create. So that's your stopping condition. For example, if you want to create 5 clusters, so you can define as I need 5 clusters, so you will be your first supercluster, second supercluster, and then 3 more clusters inside those superclusters. So those make you the 5 clusters. Initially you had 2 superclusters, and you can keep subclustering until you reach number of clusters you need to achieve. So that's what we do in the divisive method or top-down method of hierarchical clustering. This is the elbow method to find optimal number of clusters. If you are given a problem, you don't know initially how many clusters you need to divide your dataset into, or how many clusters actually your dataset should contain. That is a good question you should ask yourself. You cannot choose like 2 cluster, 3 cluster by just throwing a random number out of it. But you can do that. But if you do, you have to do it systematically. You have to experiment with number of clusters and find out what is the optimal number of clusters you can make out of this data set. If your problem specifies you to have certain number of clusters, you can safely assume, okay, if your problem specifies divide customers into 3 different segments. So that's the 3 is your number of clusters. But if you don't have that information, or if you don't have a way to find out how many clusters you should have, so you have to apply some methods. The elbow method is one way you can find the optimal number of clusters you can have in this data set. So let's explore how we can use that. So in this method, the d-bar, we call it a mean distance to each point from the centroid, as you see in this slide. In the orange cluster you have that in green color, in the blue cluster you have that in purple color. So that's the distance between each point from the centroid point or center point of the centroid. Centroid means the center point of the centroid. And then you can plot d versus number of clusters you have. So you have 2 clusters, and then you can find the mean distance to each point from the centroid. So based on that, you can keep increasing number of clusters, and you can plot this d bar versus k. K is number of clusters. So when you find this elbow point, so this elbow stand for the actual elbow. If you bend elbow a little bit, you have this shape. So this bending point you can choose. In this case, the bending point is 3, so that you can choose as the optimal number of clusters. So that k value of k occur at the elbow point. So this 3 is the elbow point in this diagram. Okay. So this is your elbow. Evaluating clustering models. When we are doing clustering from any real data set, we cannot assume all data points should be in a cluster. We cannot force it. So maybe not all data points need to be in a cluster, so because real data can have noise. In ideal clustering, what we need to do is we have to minimize intra-cluster distance. We call it cohesion. So what does that mean? The distance between the center points and the each data point within the cluster. So your data points should be close to each other. So that's the intra-cluster distance. And what we need to maximize, you have to maximize the inter-cluster distance, the distance between 2 clusters. If the distance between clusters are far away, and the distance between the items or the data points within a cluster is close by, so that is a good clustering. So inter-cluster distance we also call separation. Intra-cluster distance we call cohesion. I hope you understand those 2 concepts now. 2 approaches to evaluate clustering models. We can apply domain knowledge. If you know what is happening in the domain you are trying to analyze this data from, you can apply that to understand how good is your clustering model works. You can apply other mathematical methods. So those are like data-driven methods we can explore. You can find within cluster variance for different values of k. So you can, same as the elbow method, you can vary a number of clusters in your algorithm and you can find within cluster variance. This Silhouette coefficient is another way of determine how good is your clustering model work. So that's a value between -1 and +1. To do that, you have to consider mean distance between points within each cluster and mean distance between a point to all other in the nearest cluster. We will have this in a diagram, so don't worry if you don't read it properly in the slide. If you get the value -1, it's the wrong way of clustering, so maybe you have to revisit. If you get value is 0 or close to 0, its overlapping can be seen, so the two clusters are not well separated. And if you get +1, so clusters are well separated. So this is how you can determine whether your clustering worked well or not. This is how Silhouette coefficient or cluster quality we can use in our cluster evaluation. So in this diagram, you will find A is mean intra-cluster distance or cohesion. B is mean inter-cluster distance or separation. Let's see in the diagram. So this is A. For each point, you can define AI, the distance between each data point with the other data points, and you can find the mean value of that distance. You can find it for all other data points in the cluster that define intra-cluster distance. Okay, so the same thing you can find for B, so the other cluster, and then you can find the B value for the mean intercluster distance. So that's the separation, how you define how far your cluster, your data point from each cluster, other clusters, right? So the BI bar, it will define the mean intercluster distance. For every point, we can find the Silhouette coefficient as I is bi bar minus a bar divided by max value of a bar and b bar. Then we can get the average of the coefficient for each cluster. This is a computationally expensive method. As you see in this diagram, you have to compute distance, a large number of distances between each data points within cluster and each data point with data points in other clusters. So this is a computationally expensive method, but in this way you can, if you want to determine how good is your cluster, you can do that. To find the best number of clusters, you can compare the coefficient with number of clusters. You can plot it, and same as you do elbow method. Points with the lowest coefficient are border points, or potential outliers can be detected. So points with the lowest coefficient, we can consider them as the outliers for your data set. Lesson recap. In this lesson, we discuss about clustering algorithms in general. We learn two types of clustering algorithms, hierarchical and non-hierarchical. For non-hierarchical clustering, we explored centroid-based clustering, and we get an example of k-means clustering algorithm. And then we looked at distribution-based clustering, we got example of Gaussian mixture models. And for density-based clustering, we explored dbScan. And for hierarchical clustering, we explored two different types, agglomerative and divisive, where you can go with the bottom-up approach or divisive approach. Then we looked at how we can use elbow method to find optimal number of clusters, and then how we can use Silhouette coefficient to find the cluster quality. In the next lesson, we will explore how we can use scikit-learn machine learning library to build clustering models. We will use the familiar dataset we use for classification, which is iris flower dataset. We will use features from that dataset to group flowers into different clusters. We will be exploring different types of clustering algorithms in the scikit-learn library, and we will do hands-on exercise with the Jupyter Notebook. See you all in the next lesson.